All right. For the final talk of the workshop, we have Binyamini talking about unlikely intersections in the irregular context.
Okay, thank you, Jacob. Okay, so I want to talk about some applications of O-minimality to unlikely intersections, but in some new kinds of contexts. So I'll actually present two different problems, and I want to convince you that we can access these problems using O-minimality, and a lot of the things that show up when we are doing unlikely intersections for O-minimality, like there's the Pila counting theorem, there's some functional transcendence result. So all of these things kind of come up, but in a different way. So I'll start by talking about two problems. And the first one is about orthogonal polynomials. So I will not assume that you know what they are. So let me give a very brief definition for what are orthogonal polynomials. Okay, so in general, we are talking about the sequence of polynomials, Pn in x, where n ranges over the integers. I mean, okay, I'm looking at ones with q coefficients in general. I mean, this is the stuff of analysis, and in general, you take out coefficients, but it doesn't really matter. Okay, so I want to have the degree of Pn Bn. I want to normalize them somehow. So a common normalization is to put Pn of 1, for instance, to be 1. Although, I mean, this kind of depends on the specific sequence that you consider. And finally, I want to have some orthogonality. Okay, so the orthogonality relation depends on the sequence that you consider. So I want that for every m not equal from n, I want to have that the integral over some interval Pn Em is equal to 0. Times some weight. Dx. This is Pn of x, x is equal to 0. And now for different weights, different intervals, we'll get different families of orthogonal polynomials. So a few standard cases that I will kind of mention are so first is Legendre. So here we take I to be minus 1, 1, and the weight to be 1. Okay, so that's maybe the most classical one. It's called Legendre. It could have also been named for Gauss, because Gauss used this for the so-called Gaussian quadrature, for a way of integrating functions and improving the accuracy of numerics. But anyway, this is the Legendre one. I'll also talk a bit about Laguerre, where you take I to be 0 infinity and the weight to be e to the minus x. So this comes up in physics a lot. And I'll talk about Hermite. So Hermite are actually closely related to Laguerre. Here you take I to be all of the real line, and the weight you take to be e to the minus x squared. 2 maybe, but e to the minus x squared. So this comes up in, let me say x squared, just to fix my definition. So this comes up in probability. Okay, so these are some sequences of very classical orthogonal polynomials. And the first question I want to kind of consider is actually, I learned it in a letter from Steepest to Hermite. I wish I could remember why I was reading this letter. I think I found it in a math overflow question. So there's a letter from Steepest to Hermite. So this was in a letter of 1890. Okay, and what he asked, I cannot reproduce the French, but basically what he was asking is, can Pn, by the way, let me add the letter. So this one is usually called Pn. So I'll keep Pn. Laguerre, I'll use ln, and Hermite, I'll use hn. Okay? So, I mean, Stieltjes was really asking about the Laguerre. They're the most, sorry, about Legendre. They're the most classical one. So he was asking, can Pn and Pm share a root except 0? Okay, for n not equal to m. So we have this collection of polynomials. This is a degree n, this is degree n. So they have n and m roots, and can two of them happen to be the same? 0 occurs for every odd one because they are odd functions. But except for 0, it's not clear. And so that's one thing he asked. And then he said, well, I don't know how to prove this. Maybe Pn is just irreducible. I mean, again, except for this. And both of these are completely open. Okay, so people have looked a lot at the Galois groups of these things, the reducibility of these things. It comes up. I mean, these roots have meaning in number theory. We don't know if they're irreducible. We don't know if they can share roots. Basically, nothing is known.
There are few results from a student, I'm sure, about 100 years ago.
Yeah, I looked at those results, but they don't establish irreducibility. They don't.
Maybe if n is a prime number, something.
Yeah. I mean, definitely people looked, and there are known results. I mean, there's no kind of something that looks like a solution to this. People looked at different cases. Things are known about how it can be decomposed, and the Newton polygon of this modulo different prime. And people looked a lot, but the questions are completely open. Okay, so this I would like to argue is an unlikely intersection problem. Okay, we have two polynomials. We want to share a root, and we should try to address this using O minimality if we can. Okay, so indeed you're ahead of me, but I was going to say that Shu actually he looked at this and he proved that Ln, for example, so Hn is irreducible. Again, except for this issue with the 0. So for these guys, this question is easier. Okay, so these two guys are reducible, so they don't share a root, but that's kind of a simple type of unlikely intersection problem. We could ask a more complicated unlikely intersection problem. Okay, so
Why is it easier?
yeah, I mean, because they're irreducible, then okay, they cannot share a root because this is.
No. Why is it easier to show that?
I mean, there are formulas for this. There's a million formulas for these guys. So these formulas, binomial coefficients appear, and you can try to do this kind of mod p reduction and see what you know about the Newton polytop. And it just turns out that for this, you get some nice conditions on the primes that divide the coefficients, and for Legendre, you don't. It's a very kind of careful manipulation, and then people try to do something similar for Legendre, the student of Shu, whose name I forget. And yeah, but it somehow doesn't work for Legendre the same way it does for Laguerre and Hermite. Okay, so now I want to make an unlikely intersection kind of philosophy problem here. So basically I want to model it after Underholt or Manin-Mumford. So I'm going to define special varieties. Okay, so I'll do it for Legendre for just to pick one. So call V in Cn. So I'll do it for Laguerre. Laguerre special if given by, so either xi is equal to xj or xi is equal to r, where r is the root of Laguerre, where some Laguerre k of r is 0. Okay, so I mean, the roots of Laguerre, they replace the role of torsion points or CM points. And I mean, I'm claiming that the only upper special conditions are just equality. So it's kind of a question specific to the polynomials you're looking at, but okay. We don't know of any interesting formulas for Laguerre except for identity. So this is at least a conjectural statement. Then you can ask, does Manin-Mumford hold? Okay, so I'll skip to the end. So theorem by myself, Kiro and Pila is that okay, Manin-Mumford holds. Laguerre. Okay, so when I say Manin-Mumford holds, I mean, the usual set of Manin-Mumford. So take now any variety, look at all the special points in there. So all the points where every coordinate is the root of Laguerre, take Zariski closure. This will be a union of finitely many special subvarieties. So we kind of understand the Zariski closure of all the Laguerre roots in a variety. Now I should make some comments about this. So make a comment. So actually, after we showed this in Haifa, we learned that this particular case, there is a simpler proof. Okay, so actually what Shul showed is that the Galois group of Ln is equal to the entire symmetric group. And in this case, cadets and the Barry Sorker have another proof. So basically, it's easier because you have only one polynomial with each symmetric group, so it's too simple. But if I were to throw in several families of polynomials and they would all have Sn, then it would already become more complicated. Whereas our approach, I mean, as you'll see, it's really following the Pila-Zania method. It would work kind of in greater generality, but I just want to formulate something simple that I can show.
Is the cadets first result just for any family of polynomials?
If you have a family of polynomials that are all Sn or maybe An, then you can prove it. But if you take, let's say, two families, and so you get Sn twice, then you already have to analyze the conditions between them, and then it's not so clear. So anyway, but I mean, I really want to focus more on the kind of ideas of how omnimality is related to this kind of situation.
But you're saying there's a general theorem for a sequence of polynomials where each group is Sn?
Yeah. Yes. So this kind of theorem, it holds when you have if you have a sequence of polynomials, exactly one of each degree, and it's Sn in each degree, then you can prove this kind of, I mean, same kind of statement that I made here. And it's a very simple proof. Okay, now so I'll talk about this. I'll also talk about some partial results. Partial results for Legendre. Okay, so we using this omnimal approach, we cannot prove the case of Legendre, basically because Legendre are not known to be reducible, but we can still get some partial results from Legendre. I will explain those. Okay, but now I want to go to another kind of problem. So this was one problem. Second problem is about harmonic analysis.
So you didn't say what happens for Hermite.
What happens for?
Hermite.
Hermite is the same. Sorry. Yeah, I mean, this works for Hermite. Basically, our approach will work for any family of orthogonal polynomials if you know irreducibility, or even if you have a Galois orbit lower bound. So we need to know that we have a lot of Galois conjugates. Not as many as irreducible, but just some power of the degree or something. Yeah.
Is it necessary with the orthogonal polynomials, or do you think just any sequencer?
It's not necessary that they would be orthogonal polynomials, but I mean, as you will see, it uses some kind of stuff.
But I'm just asking about the truth, right?
I mean, when you see how the approach goes, you will see it needs to be polynomials that admit certain kind of asymptotic expansions that are definable. So it happens for orthogonal polynomials, but for very deep reasons. So, I mean, definitely happens for many other sequences, but not for an arbitrary sequence. Okay, so let me talk a little bit about harmonic analysis, unless there are questions.
Yeah, can I ask a simple question? So can you repeat the definition of unlikely intersection? All V Laguerre special is?
If the V is given by either equalities
Yes.
or setting some coordinate to be equal to a root of Laguerre. Right, so just like if you're doing, I mean, this replaces the isogenies. I mean, if you're doing under Ort, right, then instead of having all the modular relations, I just have equality because there's no modular relations here, or I have like the CM points. So now CM is replaced.
Yeah, and the R is necessarily on the first variable.
I mean, it's xi is equal to r. So you can take, yeah, sorry, you can take any coordinate to be a root. Yeah.
Okay, thank you.
Okay, so the other kind of problem I want to consider is in harmonic analysis. So it's a question by Fugleding. So I'll first make a definition. So I'll call lambda in R2 how did I want to phrase it? Orthogonal for D. D is the unit disk. Basically, if the corresponding exponents are orthogonal. Okay, so I want the integral of e to the 2 pi I lambda 1 minus lambda 2 times u du to be 0 for every lambda 1 equal to lambda 2 in lambda. Okay, so it's kind of a set of Fourier characters that are all happen to be orthogonal when you restrict them to the disk. And Fugleding thought a lot about this kind of orthogonal sets. He has a conjecture which is false in general that a set is tiling R to the D if and only if it has an L2 basis of orthogonal exponentials. And this is kind of the origin for looking at this, but Fugleding asked the question specifically for D. D is definitely not tiling the plane. You cannot tile the plane with D. So we thought that, okay, there shouldn't be an orthogonal basis. That's not very hard to see. And he made the following conjecture. Or
Is the integral is over?
what? The integral is, oh, sorry, over D.
Yeah.
So thank you.
The unit disk.
Yeah, D is the unit disk. Yeah, so this D is the unit disk, and we're looking for things that are orthogonal on the unit disk. Okay, and then the conjecture by Fugleding from 74 is that for any such set, the number of elements is less than 4. Okay, there can be no more than 4. I'll kind of when I reformulate this as an unlikely insertion problem, you will see why it is 4, and I mean why he had the natural reason to think that 4 is the number. And yeah, when I formulate it, you will see that this is it's not really a question in harmonic analysis, it's a question of transcendental number theory. Okay, so this is a question about algebraic relations between certain transcendental numbers. It's probably very, very difficult. Okay, so let me say a bit about why this is connected to transcendental number theory or to minimality. Okay, so for that, I have to introduce the Bessel function. J1 of x. So this is a function which satisfies the following differential equation. And y prime plus 1. So it's a solution, okay, one of the 2 independent solutions. It kind of looks like a cosine that slowly degenerates to 0. So the interesting thing about this function, the reason why Bessel got that name for him, is that if you take the characteristic function of D and take Fourier transform, it's essentially Bessel. Okay, so so if you evaluate lambda, this will be basically Bessel of 2 pi lambda divided lambda. If I did this correctly. So essentially, after some normalization, this is lambda. So I'm claiming that this question that Fugleding asked is really a question about zeros of the Bessel function. Okay, because I mean, here I'm basically taking the Fourier transform of the characteristic function of t and evaluating on these differences. Okay, so if I call this condition star, when I'm saying that star is equivalent, the question of Fuglet is equivalent to okay, something like 2 pi times these distances, lambda 1 minus lambda 2, being a root of Bessel. For every lambda 1, lambda 2. Okay, so this is an equivalent. So he was motivated by, Fuglet was motivated by this, and he was saying, well, we should not have any algebraic relations between roots of Bessel. They should all be transcendental. And this will imply this conjecture. So let me show you why. So I'll make a small definition, the notation, denoted by V42. This is in R6. This will be 6 tuples of distances between 4 points in R2. Okay, so I'm taking 4 points in R2, then there are 6 distances, and I'm looking at all the 6 tuples of distances. Why 4? Because this is the first case where this variety has a risky closure strictly smaller than R6. But this is a semi-algebraic variety, but it actually satisfies some actual polynomial relation. Okay, so this is not open in R6. And therefore, the question about this question was the same as saying, I want now a 4 tuple, I want lambda, which is a 4 tuple, such that all the distances are going to be roots of Bessel. Okay, so I'm saying there's another kind of unlikely intersection problem here. Fuglet is basically saying, no Bessel special points in V42. Okay, where Bessel special is the same as this Laguerre special, but now instead of roots of Laguerre, I'm taking roots of Bessel. Okay, and you can check that actually there are no special subvarieties in V42, positive dimensional. So really it's a question about points, and Fuglet was saying that we should not have any special points here. So we cannot prove this yet, and I think it's probably very difficult. I'd say that the roots of the Bessel function, each of them separately is transcendental. And this is a result of Siegel. It's maybe one of the reasons why Siegel invented the theory of if functions is to prove this. It was also connected to a question in harmonic analysis on the disk. So it's known that each of them is transcendental. Even for 2 of them, getting that they're algebraically independent, it's probably way out of reach. So yeah, I don't see a way to really approach the full Fuglet conjecture. But let me tell you what is known and what we can do. So what is known? So Fuglet, maybe in the paper where he asked the question and more explicitly later, he gave an argument showing that every lambda is finite, at least. You cannot have an infinite set of orthogonal exponentials. But it says nothing about the size of lambda. And then people try to get some estimates for at least the density of such a set lambda. So the Savage and the Zakis, they got that if you count the number of points in lambda intersected with square of radius r, so we are kind of looking at such a lambda, but only counting in a box of radius r, the number is going to be less than r to the 2/3. And then recently, maybe last year, I think, Zakharov kind of refined their method with a much more complicated combinatorial geometry. And he was able to show that, okay, the same number is less than or equal to R to the 3/5 plus epsilon for any positive epsilon. Okay, so that I think is the best that is known about this. So now my
3 possible?
is what?
3.
3 is definitely possible because 3, you see, I mean, any distances you can realize. So let's just pick 3 like Bessel zeros that satisfy the triangle inequality, then we can realize all the distances as okay. So yeah, so this is the best that is known. What I want to kind of, before getting to the theorem, I want to say that, okay, if you think about this as a no minimal counting problem, we're kind of thinking that the Bessel zeros, they're special points. They should be in correspondence with some rational points. We should be translating this variety to some transcendental variety, counting rational points. And if this were possible, it would mean that we should get out to the epsilon here. Or maybe with better counting results, poly log out. Okay, so this is the theorem. So this is me and Kiro, and also Gadi Kozma and Jonathan Pila. Yeah, so we prove that for V in CM, the number of kind of maximal special subvarieties in V intersected with a ball of radius R is O of what? Of V and epsilon out to the epsilon. And so this kind of what you expect from Pila, and as usual, you can make it uniform for V of a given degree, same as you usually get with point counting. Okay, so but I mean, the message of my talk is not necessarily this one of these theorems, it's kind of the approach. The idea that you can actually touch these things using all minimality, and you can apply this, I mean, the kind of things that you expect to get from Pila, you can get in this context as well.
So a stupid question.
Yes.
You translate it to the small monometric term, you get out of the epsilon, or?
Yeah, it's in fact it's stronger because they were just saying that in a set there's we are saying there are only out of the epsilon 4 tuples that can even, I mean, we are kind of counting counterexamples to Fugledes. We're counting 4 tuples of points and we are saying there's very few of them. They're saying only kind of for a given set lambda, you can get only this many. The number of 4 tuples, then you can compute what it would be, but it would be like this to the power 4. Anyway, I mean, so ours is in some sense a bit stronger than these, even, I mean, even if they had out to the epsilon here, ours was still be stronger. Okay, I think that probably with work, this can be improved to polylog R using this kind of sharp counting methods, but we have not gotten that far. Questions? Okay, so, yeah.
Maybe you'll say this already, you've said it. So do you just need some sort of differential equation, or like what is the easy thing you can say beyond just Bessel?
Good question.
Okay.
So I'll show some, yeah, I'll show what I need exactly, but okay, I thank you for the question. I did forget to mention that this equation, okay, it's quite similar to the equations that we often deal with in, I don't know, algebraic geometry, except for one issue. I mean, it's a nice equation, it's linear, it has polynomial coefficient, it has a regular singularity at 0, but it has an irregular singularity at infinity. Okay, so as we learned from Stoke, it's not going to be definable. Okay, so kind of whether or not this should be related to minimality at all is kind of surprising.
It's like you said, it's possible.
Yeah, it behaves like
It can't be different.
exactly. So I mean, so
Is irregularity of
it's I think this one is rank 1. But I mean, but that is not so crucial for us. So we also looked at the Airy function where I think it's rank 2. I mean, irregularity is not a major obstacle, but I mean, we need something else. Okay, so the question is, does minimality even play a role here? So let me just give you a little drawing for this. Well, J function, as I said, it looks like this, something like this. this is this J1, the Bessel function. And the orthogonal polynomials, it's kind of even worse because they look like this, and this, I guess this. Now this is P, 1, 2, 3. So I mean, this picture gets more and more complicated. It's not that it's definable for some G%. Actually, all the roots are in the interval. They become equidistributed in the interval with respect to a certain cosine law. So I mean, this is really a picture that becomes more and more oscillating as you increase the parameter. So it's definitely not a definable picture. Even, I mean, in Helene's talk, she said, I know nothing about trigonometry, but definitely it should not contain oscillations, right? So definitely this is not something that we would normally expect to. Okay. Okay. Okay, so why can we do anything? And let me start with the Bessel case, which is slightly simpler. So I'll give you a theorem. And this theorem maybe for me is the main content of this talk. So this is the surprising thing. The rest kind of follows by following the analogy. But there is a definable f from R to R, mapping integers to Bessel zeros. Okay, so there is something like these uniformizing maps. I mean, usually we have, I don't know, you want torsion points, you uniformize with the abelian function, and then you map torsion points to integers. Now you can use Pila. I'm saying same thing happens here. We have this interesting discrete set of Bessel zeros. You can map them with some definable function to integers, and then you can try to count with Pila.
So definable in which setting?
Excellent question. So this is not in Rnx, but rather in Rg, this multisummable that we heard from Helene and then Patrick.
It maps to Bessel zeros, you mean it's surjective to Bessel zeros?
Yeah. So it really
It's
maps
1 to 1.
all the this nice one is really 1-to-1. It maps all the positive integers to all the Bessel zeros. Okay, you can also do negative integers to the negative Bessel because we are always looking at the positive ones because it's distances, so we might as well restrict the positive ones, but it's all symmetric. But I mean, the fact that it's 1-to-1 is not so crucial. Like what mainly we want is to be able to take a set that we're interested in, pull back under some function, and know that in this pullback we are just counting integers or rationals or something like that. Okay, so why is this?
What is analytic?
Is the map analytic? I mean, it is analytic inside R, but on the boundary of R, it's not analytic, and it's not even definable in R and X. So you cannot get it from analytic and X. So what is the function? Let me.
Sorry.
Yeah.
So there's no kind of Galois here. Like it's not like you need to say that like the height of the integer is somehow.
Oh no, I do. I mean, I do want to say that all of the integers, let's say up to R, all the Bessel zeros up to R will be parameterized by thin roughly of height R. So yeah, it will work out like this. I mean, this map is it's something like n goes to n plus little of 1 over n, and I mean it's really almost identity, well, up to some scaling. Okay.
Up to scale.
Questions?
Yeah, I love it's the identity up to scale.
Yeah, well.
It's a very nice expression.
There might be a pi in there. I set pi equal to 1 everywhere. Catch me on that.
I have another very pathetic question, then I'll
Yeah.
stop. Is the little g there as opposed to the capital G yesterday important, or that's just?
No, sorry. I mean, was it capital G? I mean, Patrick is the master for the multisummable structure, but it's okay. I mean, yeah, it's this.
Plus a calligraphic G.
Well, yeah, this is my attempt at doing a calligraphic.
Okay.
Pathetic attempt. Okay, so the proof is basically okay. It's not really, but let me say it's basically due to Delvaux and Laplace. because what they did is they gave an asymptotic expansion for the Bessel function. And the asymptotic expansion looks like this. J1 of x equals e to the ix times some g1 of x plus e to the minus ix times g2 of x. Okay, so these are oscillating terms clearly. We have e to the x. These are responsible for us having a lot of zeros. These things, on the other hand, are definable in RG. So these two, definable in RG. Let me switch to a big G for you. So, well, this is not exactly what they showed. What they showed is an asymptotic expansion. So there is, you can find a formula like this, 150 years old, where here you have some sum, like a sum of an divided by x to the n. Okay, but this sum does not converge. And if you look at the size of the coefficients of this sum, and you know the other definition that Patrick did not give, for multisummable, it seems like this sum would be the sum of a multisummable function. But I mean, to really check it, you have to know a lot more. You have to know that these things continue analytically to a big enough domain, and you have some bounds, and they do. Okay, so I will not go into the details, but so these guys are actually definable, and you have this like formula that separates for you some oscillating stuff and some definable stuff. And I'm claiming that whenever you have this, you can play this game of mapping integers to zeros, for instance. And the way we do it, okay, I'll say basically that the graph of f, you can write it like, okay, I want all the t's and x's. So I'll map t to x, and then I want that the, where do I have my inequality? Yeah, I want x minus t to be between 0 and 2 pi. So basically, t is like the thing that will translate me back into the standard fundamental domain. And now, instead of writing this formula, I write the same formula, but I write e to the I x minus t. Maybe I should put 2 pi. 2 pi t. Let me ignore the pi, okay? I'm assuming pi is 1, just to keep things simple. g1 of x plus e to the minus I x minus t times g2 of x is equal to 0. I mean, I played this stupid game, but what it means is that now I'm evaluating this non-definable thing only between 0 and 2 pi. Okay, so this formula that I wrote here is a definable formula because I'm evaluating between 0 and 2 pi, and this is still definable, right? I said it's definable. So the only thing that I pay is that now I'm not defining the whole set. Rather, whenever t is an integer, I will get the original set, right? Because when t is an integer, this formula is equivalent, well, up to the fact that I erase the pi. But if we ignore this pi, then, I mean, this formula for integer or for integer multiples of pi, it's equivalent to the original formula. Okay, so for every integer, I will indeed get a Bessel 0. And for every Bessel 0, I will get an integer. I should just choose the particular integer that maps me back to the standard fundamental domain. So this is very easy, very similar to how Jonathan proved functional transcendence. It's kind of the same idea. Okay, so this is how it works for Bessel. I want to also say something about the orthogonal polynomials case. Orthogonal polynomials case, it's, yeah.
So there's this whole theory of Bessel polynomials from Grossman. Does that have anything to do with this?
It also fits. So it's, I mean, the way that you can handle Hermite and you can handle Laguerre, you can also handle Bessel polynomials. I mean,
But it's irrelevant. It doesn't address this at all.
but I think it's related for sure. I mean, all these asymptotic expansions are related, and I mean, what is needed is an asymptotic expansion like this, but now with polynomials. And with polynomials, it's somehow a bit different because we have two parameters, right? So Bessel, it's just, we have, I hid, there is actually another parameter, I wrote J1 here. You can ask what happens when you move this one. That's something that Ziegler did. It's a very interesting question, but I will not touch it. but it does fit in this picture. So, but I will touch the case of moving parameters when we're doing with orthogonal polynomials. Okay, so for orthogonal polynomials, I want to say that there's a similar theorem where, so there is a definable. So now it will be a map from R2 into R. Mapping n comma nu to the new root of Pn. Okay, so I'm claiming you can do the same thing with, let's say, this Legendre family, or I mean, I'll say what happens with Hn and Ln, but you can map now pairs of pairs of integers to the roots of Pn. This is a little bit similar to torsion points in a binary variety, except in torsion points, it all comes really from a one variable thing where you have to divide. I mean, the torsion points are the things that go to a rational number. We don't think it's true here. So we don't think you can find a definable function taking rational numbers to the roots of Pn. You really need kind of two independent variables, but except for this, it's quite similar. Okay, so what is a proof of this? Sorry. Here I wrote the Regula plus, this was wrong. I knew something was funny when I was writing it. This is not the Regula plus, this is Poisson-Jacobi. So while I was making this talk, I started playing this game of like a bingo of 19th century mathematicians who wrote these formulas, and I got almost all of them. By the end of the talk, you should see every name you know. So this one is the Regula plus. The Roux and Laplace, they gave an asymptotic formula for Pn. Okay, but now it's a complicated asymptotic because there are two variables. It's not the same as before. We have here, I mean, we have the n of the index of the polynomial, but also we should evaluate the polynomial itself. So there's the variable of the polynomial. So what their nice formula says is that Pn of cosine theta, I'm reparameterizing instead of x, I take cosine theta. It's nicer that way. This is e to the I n theta times g1 of n and theta plus e to the minus I n theta g2 n and theta. Okay, these two, they are again going to be definable, but there is a little problem. So they are definable in R times K, where K is a compact inside -1, 1. Okay, so we feel that this is probably just a technicality. So, I mean, currently, we get that these expansions are algebraic when you restrict the second variable to be some slightly smaller thing than -1, 1. Okay, for our considerations, it doesn't really make a difference, but just there are some issues here. Probably around the endpoints, there's a different asymptotic expansion. Okay, so you need to maybe play around a bit more. I will not write these. So okay, once you have this, again, you can add integers to kind of n is one integer, and then I'll add another integer u to scale this back to the standard fundamental domain, and then I'll play the same game. Okay, maybe let me even call this one. This one will be FL or FP. This one will be FB. Just it's kind of uniformizing for Bessel or for Legendre, and I have similar ones for Laguerre and for Hermite.
Is there some kind of irregular differential equation with parameters?
That's a good question. So I will write the equation for Laguerre, for example. But with Legendre, the equation is not irregular. Legendre satisfies a regular differential equation. But the irregularity here is the dependence on the parameter. So what we are doing is moving the parameter of the differential equation. That's why I think this kind of thing might be interesting for doing, trying to understand how monodromy changes with the two parameters. The dependence of the solutions of equations on parameters, it's usually kind of, you should think about it like an irregular singularity. Okay, so for Hermite, and also for Laguerre. Hermite and Laguerre are closely related. They fit in the same kind of family if you introduce an extra parameter. We also have something like this due to Perron and Fair. However, that's not good enough, because what happens with Hermite is that because the interval is from 0 to infinity or minus infinity to infinity, then the roots become kind of equidistributed on the whole of R. So if you restrict a compact domain here, you don't really describe enough of the roots. So this is a known issue in the theory of orthogonal polynomials, and there is actually another formula due to Plancherel-Rotach, where you rescale the time. So I mean, this kind of gives you an asymptotic not for a hn of x, but rather for hn of square root of n times x. Okay, so it makes a certain rescaling of the time, and then you really can describe enough of these roots. So I will not go into the details, but I mean, just trust me that for all of these orthogonal polynomials, and in many other cases for confluent hypergeometric functions and for general linear ODEs of degree 2 with respect to parameters, you often have these kind of asymptotic expansions that are supposed to actually be definable in RG. But I mean, I did want to mention that checking this was relatively easy. I was able to do it by hand to check that they're actually definable in RG. Checking that these guys are actually multisummable is not easy at all. And I asked several experts, and eventually our co-author Avner Kiro managed to do it. But I mean, this really requires some serious analysis. So, I mean, if you're going to go in this direction with, you know, introducing parameters and differential equations, then you have to get an analyst to do the hard work for you. Yeah, okay, so what's the strategy now? So let's say I want to do this Bessel one. I'm going to take, so given V in Cn, I define a Z Bessel to be, I'll take this Bessel uniformizing map, pull back V, and then I want to apply Pila-Wilke here. Okay, that's what I should do. And if I can apply Pila-Wilke, then it will give me a bound on the number of integers here, which will be the same as a bound for a number of Bessel zeros in V. That's the way it usually works. So what Pila-Wilke will tell us is that there are few Bessel zeros in V unless we have an algebraic part, right? So unless ZB alg is not empty. So the question is really, can we understand the algebraic part of this thing? And here it really helps that we have a differential equation for Bessel. Okay, so for Bessel we have a differential equation, and we should kind of solve the functional transcendence problem with respect to this Bessel. So let me tell you a theorem that solves this functional transcendence problem for Bessel.
So there is Bessel.
Hmm? What?
We just had Bessel here.
Oh, sorry. I'm also not very good at this blackboard management. Yeah, so basically, I mean, what I want to say is that I define special varieties, weakly special varieties, and you know, this algebraic part is going to correspond to the union of weakly special subvarieties, just as it does in the classical situation. But to prove that, you need an Ax-Lindemann theorem, and you might as well go ahead and try to do an Ax-Schanuel instead. So I claim that there is a Bessel Ax-Schanuel theorem, which says that if we take the transcendence of function fields where I fix some T1 up to Tn and their exponents, and then also I take x1 up to xm and their Bessels, this is going to be at least n plus m plus 1. Okay, so it's kind of the same as you usually have from Ax-Schanuel. Okay, unless one of two things happens. Well, so either there is a relation between these exponential parameters, so t1 up to tn are linearly dependent over mod constants. Okay, so that's one case. Well, or xi is equal to plus or minus xj. Or I not equal to j. So kind of the only reasons why you would get some algebraic relation between these functions are, I mean, either the known relations between the exponents or the known relations between the Bessels. Actually, we have a more precise form where you add the derivatives of Bessel as well, and you predict the exact kind of transcendence degree of the differential closure of this. But I mean, this is kind of enough. Okay, so let me say a little bit about the proof, or why can you prove this kind of thing. So we use, well, one thing that maybe the main thing that we use is this like differential algebraic criterion for the Ax-Schanuel. So there is a work of what are the names? Blasquez-Sans, Blasquez-Sans, if Freitag was here, Naglu and Kassab. Oh, sorry, I forgot Kassab. So they basically show that you can, whenever you have the situation, okay, you need something which is called the sparse differential Galois group, and here it happens. The differential Galois group for the Bessel function is SL2. And well, for Bessel it is SL2. So we are able to apply the result. And then we also use some work of Kolchin that reduces you in this case to pairwise dependencies. So it's basically this Mursal lemma tells you because the differential algebraic group is a subset of some power of SL2, any kind of relation that you can get has to involve a relation between two of the coordinates. And then for two of the coordinates, you just need to really compute the differential Galois group. And this is just some kind of explicit computation. So we know how to find the differential Galois group for irregular singularities. It's generated by monodromy and then two other things called exponential torus and Stokes phenomena. And we could just compute it by hand here over an algebraic curve, and we can see that the only algebraic curves that are special in two variables are xi equal to plus minus xj. Okay, so this is what leads to this theorem. Okay, so this is what happens for Bessel. I want to talk a little bit about what happens with orthogonal polynomials because it's similar but different. And I think it's kind of a good direction for trying to generalize this functional transcendence business. So when we do it for orthogonal polynomials, let me first state a theorem. So for orthogonal polynomials, so there is an equation. So for fixed k, we have an equation that looks like x. Let me do it for Laguerre. Lk double prime. Where's my equation? Plus 1 minus x Lk prime of x plus k Lk of x is equal to 0. Okay, so you see these LKs, they satisfy differential equations, but moreover, it's a family of differential equations where k appears as a parameter. Very simple. It's actually just they're kind of the eigenfunctions, and k is the eigenvalue. Okay, so we have a differential equation. We can kind of try to repeat what I said before. I mean, we have a differential equation. We can use this game, and then I want to say that the theorem should say so. Theorem should say, so now it's Laguerre Ax-Schanuel. It should tell us that the transcendence over C of x1 up to xn, and e to the x1 to e to the xn, and lk1 of x1. So I'm taking different parameter, lkn of xn. So this is going to be at least 2n plus 1. Okay, unless we are in some, so unless so either you have a linear dependence as before on the x's, so if the x's are linearly dependent over q about constant, then you'll get a problem. And we have one more thing. When we have xi is equal to xj and ki minus kj is in z, or xi is minus xj and k1 plus ki plus kj is in z.
Well, I thought K was an integer. I'm confused.
Yeah, so I wrote it this way, but I'm cheating. I wanted to see if anybody would notice, except for Jonathan. I mean, okay, so I mean, what I wrote here doesn't really make any sense because these are polynomials, right? LKs are polynomials. Transcendence degree of this is definitely not going to grow just because I added a bunch of polynomials. So it's completely wrong. But what is true is that this is for our kj's should be in C minus Z. Okay, so you see this is a differential equation, and I can solve it for, I mean, it's just a differential algebraic condition. I can do it for solutions of L of this equation when I take K to be anything. Usually these things will be transcendental functions and they will have a big differential Galois group and everything will work. But for the integers, which are the ones that I want, it will not work. It has a very small Galois group because it has a solution which is a polynomial. Okay, so it's never going to work. I claim that nevertheless, this is enough for us. Okay, so there's two things to notice here. First, if you're trying to understand the algebraic part with this map, we are also moving n. Okay, and we have no idea about how to get functional transcendence when you're moving n. That's not described by the differential equation. It's described by varying parameters of differential equations. It's a very deep problem. However, if you're trying to do one in Mumford, it's really enough to fix n. It's kind of enough for us to fix some n because, I mean, let's say we're doing it for Laguerre. We know that once you have one Laguerre root, you're going to have a lot of Galois conjugates, and they're all kind of for the same n. So you don't really have to count with different n's. It's enough to count for a fixed n, and then you can try to use this kind of theorem. But there's this other issue, which is that the theorem does not describe integer n's at all. However, the key point here is that, so what is the upshot of this theorem? For Pila-Wilkie counting, we don't really need to describe the whole algebraic part. It's enough to exclude algebraic blocks. So we kind of need to rule out having algebraic things of the degree which is smaller than some, d, which depends only on epsilon. So we are trying to do Pila-Wilkie counting. We don't have to have a full Ax-Schanuel. We should just say you don't contain anything algebraic up to some bounded degree. Now, containing something algebraic up to a bounded degree, it's a differential algebraic condition. So you can kind of write out these equations with generic parameters k. You can say, when do the solutions satisfy some algebraic relations up to a given degree? We know that for generic parameters, they don't. So they can only satisfy them for a finite number of fixed integers. Okay, and these finite number of fixed integers we can throw because we are just trying to, we're trying to prove Mumford, so we don't care about finitely many fixed polynomials. They have finitely many fixed roots. So actually, you can use this to kind of test the generic case, and therefore this theorem will give you what you want. So I think it often happens when you're doing like families with parameters that you have this discrete set of special parameters where something bad happens. And what this trick says is that you can look at the generic situation, get the bounds for the generic situation, and then you will be able to do Pila-Wilkie count.
So I'm confused. So this LK with K not an integer.
Yeah,
That differential equation, the solutions are no longer polynomials.
exactly. Yeah, it has the maximal Galois group. So the solutions for generic LKs are no longer polynomial. We analyze what happens for this generic LK, but then we kind of say that when you're doing an algebraic construction, then whatever happens for generic LK will also happen for the integer LK for sufficiently large integer. Okay, so having this kind of theorem for generic K, it will give us the ability to control these sets also for sufficiently large fixed integers. Okay, so I wanted to make only one other small, I don't know, in progress result. So there was the result for Bessel like this. There was the result for this Laguerre-Manning-Mumford that I mentioned. I want to go back to the question of steepest. So the question of steepest we cannot really hope to solve because we don't have irreducibility, we don't have Galois bound, so we cannot get finiteness. I'm just talking about this question of shared roots of two polynomials. So what we can probably do, so it's in progress, about the question of steepest is to show that the number of x's such that Pn of x is equal to Pm of x for a fixed, so fixed n not equal to n, and then look at the common roots of Pn and Pm. This is going to be less than or equal to poly log of n plus n. Okay, so these two polynomials, we can show that they are finitely made, but they have very, very few common roots. It grows logarithmically, like some power of log. And to do this, you should I mean, if I said n plus 1 to the epsilon here, this would almost follow from what I said so far. I mean, there was also this issue that I was restricting to a compact inside -1, 1. So, I mean, maybe if you counted really in a compact inside -1, 1 and put an epsilon here, then you can prove it from what I said. You can try to go closer to the boundary and you can try to get a polylog counting using these sharper methods, and it seems to work, but not written yet. And yeah, I'm out of time. Sorry, I'll stop here.
Any questions? I have a question actually for this original theorem you had about Legendre. You had Legendre, Hermite, Laguerre. To apply this kind of method for the Manning-Mumford, you need some Galois lower bound, right? So is that easy to get in the Legendre case?
No, so Legendre, I didn't have the theorem for I got the theorem for Laguerre and for Hermite.
Oh, you don't have it for Legendre?
For Legendre, like the best I can do is, to give a bound, which, if I had the theorem for Legendre, this would be finite, right? I would know that there are finitely many intersections. It's kind of.
Oh, I see.
But yeah, for Legendre, there's no Galois lower bound. If you could get any Galois lower bound, then you would get
You
it.
can't even rule out a Q root at the moment.
Yeah.
Okay.
So yeah, that's kind of I wanted to assign homework at the end of this talk. So yeah, for the G function people, maybe you can try to do I mean, Legendre are very nice. They satisfy the differential equations. They are hypergeometric. So if someone can prove a Galois orbit lower bound now for the roots of Legendre, this would be quite helpful.
I had one more question before we go. In this Ax-Schanuel at the end, can you add k's in the parameter as well? You just didn't care, or is there a reason you?
Can I add the parameters as variables?
Correct.
I cannot, because I mean, this is a very, I think it should be true.
Okay.
But it's a very deep problem because the dependence on k does not obey a differential equation. It actually obeys a second order difference equation.
Yeah.
So dependence on k is more like the gamma function. And I think it would be very interesting if one can somehow understand function. It is needed. I mean, when you construct these functions, this n is like my k, it appears also as a variable. So we also want to know what happens when you move n algebraically, but I don't know how to do it.
But under that blackboard where you have ki minus kj is an integer.
Yeah.
Think of that thing. So looks like contiguity of hypergeometric functions.
So what this basically says is that, so let's say I take xi equal to x, so let's just call it x. What this says is that there are some algebraic relations between ln of x and ln plus 1 of x. And this comes from this difference equation that you have. I mean, there's a difference equation that relates ln plus 1, and ln plus 2. They are connected by a simple difference equation. So this is kind of showing you that. So if you are evaluating on the same x and you differ by an integer, then there is an algebraic relation. And that holds not only for the polynomials, also for generic parameters k. So always Lk and Lk plus 1 are related by some algebraic.
Questions?
Can I ask?
If not, yeah.
The differential Galois?
So in this case, it's slightly complicated. So if you're doing it for Laguerre, it will be GL2, and we want SL2 for this notion of sparse groups. So there is a way to take this equation and like pass to a new equation where you just rescale the solutions by e to the x, and then the differential Galois group is SL2. And then you can apply all this. So really, I mean, the full theorem we stated for this different equation, which is a balance. And here I kind of formulated it slightly weaker. You can notice that I put the same variables for the exponents and for L, whereas in the other case, I put a different set of variables for the exponents and for L. That was exactly to hide under the carpet this issue that you have to rescale these by exponents to get the full theorem. But this is true as written. But if you want kind of the full version that involves all the derivatives, then you should use a slightly different differential equation.
If there are no other questions, why don't we not only thank Gal, but thank all of our speakers this week for